Hello, students. Welcome to our presentation on electrophilic aromatic substitution, a fundamental concept in organic chemistry. Benzene reacts with electrophiles due to its electron-rich nature, undergoing electrophilic aromatic substitution. Common reactions include halogenation, nitration, sulfonation, and Friedel-Crafts reactions. Electrophilic aromatic substitution involves a two-step mechanism, forming a resonance-stabilized carbocation intermediate known as an arenium ion. The carbocation intermediate rapidly loses a proton, restoring the aromaticity of the benzene ring and completing the substitution reaction. Nitration of benzene involves the reaction with nitric acid and sulfuric acid, forming nitrobenzene through the nitronium ion intermediate. The nitration mechanism includes the attack of the nitronium ion on the benzene ring, followed by the loss of a proton from the intermediate. Here are representative electrophilic aromatic substitution reactions of benzene, including nitration, sulfonation, halogenation, and Friedel-Crafts reactions. Alkyl substituents on benzene rings can be prepared by radical substitution reactions, such as the reaction with NBS and peroxide. Halogens in the benzylic positions can be replaced by nucleophiles through SN2 or SN1 reactions, allowing for a variety of substituted benzenes. Students, please note that halo-substituted alkyl groups can undergo E2 and E1 reactions, with bulky bases favoring elimination over substitution. Substituents with double or triple bonds can undergo catalytic hydrogenation, reducing the number of carbon-carbon multiple bonds. Alkyl groups on benzene can be oxidized to carboxyl groups, using oxidizing agents like potassium permanganate or chromic acid. If the alkyl group lacks a benzylic hydrogen, the oxidation reaction will not occur, as the first step involves removing a hydrogen from the benzylic carbon. Further, reagents that oxidize alkyl substituents can also oxidize benzylic alcohols to benzoic acid, demonstrating their versatility. Students, let's now explore how substituents influence the reactivity of the benzene ring. Substituents play a crucial role. Electron-donating groups enhance the ring's reactivity, while electron-withdrawing groups reduce it. Substituents can donate or withdraw electrons through inductive effects or resonance, influencing the reactivity of the benzene ring. Substituents with lone pairs can donate electrons by resonance, while those with double or triple bonds can withdraw electrons by resonance. Substituents attached to electronegative atoms can withdraw electrons by resonance, affecting the electron density of the benzene ring. Strongly and moderately activating substituents increase the reactivity of benzene by donating electrons into the ring. Moderately activating substituents can donate electrons both into and away from the ring, affecting the overall electron density and reactivity. Please note that alkyl, aryl, and CH-CHR groups are weakly activating substituents. They donate electrons into the ring by resonance and inductive effects, making them slightly more electron-donating than withdrawing. Further, halogens are weakly deactivating substituents. They withdraw electrons from the ring by resonance and inductive effects, making them more electron-withdrawing than donating. Moderately deactivating substituents, like carbonyl groups, withdraw electrons both inductively and by resonance. Strongly deactivating substituents, such as ammonium ions, withdraw electrons even more strongly. This table summarizes the effects of various substituents on the reactivity of a benzene ring toward electrophilic substitution, showing their activating or deactivating nature and directing effects. The position of a new substituent on a benzene ring during an electrophilic substitution reaction is influenced by the existing substituent, determining whether the product is ortho, meta, or para-isomer. Activating substituents direct incoming electrophiles to the ortho and para positions, while weakly deactivating halogens also direct to these positions. Moderately and strongly deactivating substituents direct incoming electrophiles to the meta position, as seen with acetophenone and nitrobenzene. Activating substituents are ortho-para directors, stabilizing the carbocation intermediates formed during electrophilic substitution at these positions. Protonated aniline shows that activating substituents stabilize the ortho and para positions, making these intermediates more stable during electrophilic substitution. Substituents that donate electrons into the ring are ortho-para directors, while those that cannot donate electrons are meta-directors. The ortho-para ratio in electrophilic aromatic substitution is influenced by the size of the alkyl substituent, with larger groups favoring the para position. Ethylbenzene and tert-butylbenzene show different ortho-para ratios in nitration reactions, with larger substituents favoring the para position more strongly. When both methyl and nitro groups direct to the same position, the product of the reaction is easily predicted, as seen with para-nitrotoluene and 2,4-dinitrotoluene. Methyl and chloro groups direct to different positions, but steric hindrance makes some positions less accessible, influencing the final product distribution. When substituents direct to different positions, a strongly activating substituent will dominate over a weakly activating or deactivating substituent, as seen with paramethylphenol. If substituents have similar activating properties, neither will dominate, resulting in a mixture of products, as seen with parachlorotoluene. Arenidiazonium salts expand the range of substituents that can be placed on benzene rings, allowing for more diverse chemical conversions. Primary amines can be converted into diazonium salts using nitrous acid, which are then used immediately due to their instability. Nucleophiles can replace the diazonium group in a Sandmeyer reaction, allowing for the introduction of various substituents onto the benzene ring. Cuprous salts are required in Sandmeyer reactions to replace the diazonium group, indicating their role as radical initiators. Chlorination of ethylbenzene can produce a mixture of ortho and para isomers, such as orthochloroethylbenzene and parachloroethylbenzene. Using para-ethylaniline and a Sandmeyer reaction for chlorination yields only the desired para-product, parachloroethylbenzene. The Sandmeyer reaction mechanism involves a diazonium, radical intermediate, which undergoes a ligand transfer to form the final product. Arenidiazonium ions can undergo electrophilic aromatic substitution, forming azo compounds with a preference for the para position. If the para position is blocked, substitution occurs at the ortho position, as seen in the reaction with paramethylphenol and benzene chloride. Azo compounds exist in cis and trans forms, with the trans isomer being more stable due to steric strain. They are used as dyes due to their extended conjugation. Aryl halides do not react with nucleophiles under standard conditions due to the repulsion from p-electron clouds. Nucleophilic aromatic substitution can occur with electron withdrawing groups positioned ortho or para to the halogen, facilitating the reaction. Electron withdrawing substituents increase the reactivity of the benzene ring towards nucleophilic substitution and decrease its reactivity towards electrophilic substitution. Nucleophilic aromatic substitution occurs via a two-step SNR mechanism, forming a Meisenheimer complex intermediate before re-establishing aromaticity. Students, please note that in nucleophilic aromatic substitution, the incoming nucleophile must be a stronger base than the leaving group, with electron withdrawing substituents aiding the reaction. Various substituents can be placed on a benzene ring through nucleophilic aromatic substitution, provided the incoming group is a stronger base than the one being replaced. With this final slide, we conclude today's presentation. Thank you for your attention. We hope you found the session both informative and engaging.